Participants, kindly mute your mic.
As the program is going to commence shortly, I request all the participants to have their mic in mute. Thank you.
Sean, sir, good morning. We welcome you, sir. Shall we start our program, sir?
Yeah, no problem. We can start now.
Yes, sir.
Good morning, everyone. It is my great pleasure to extend a warm welcome to each and every one of you to this 5-day International Virtual FDP on constructions of local anti-magic, 3 colorable graphs of fixed odd size matrix approach, organized by Department of PG Mathematics of Piyushya Krishnammal College for Women.
Today, we have gathered here with a shared purpose to engage in insightful discussions, exchange valuable knowledge, and foster meaningful connections. As we embark on this journey, let us embrace the opportunity to expand our understanding, challenge our perspectives, and inspire one another towards excellence.
May we now invoke the blessings of the Almighty, whose boundless wisdom and guidance illuminate our path as we embark on this journey of knowledge and discovery. Let us bow our heads in reverence and offer our sincerest prayers for enlightenment and success in our endeavors.
The theme of FDP holds immense significance in today's dynamic world. To all our participants, I encourage you to actively engage in the session.
Excuse me, participants, please kindly mute your mic.
Sorry for the interruption, sir. The theme of FDP holds immense significance in today's dynamic world. To all our participants, I encourage you to actively engage in the sessions, ask questions, and seize the opportunity to network with your peers. Your presence here today is a testament to your dedication to continuous learning and professional growth. And I have no doubt that you will derive immense value from this session.
I would like to call upon Dr. R. Sasrika, Assistant Professor, Department of PG Mathematics, to introduce our intellectual guest speaker, Dr. Gi Chun Law, and also address the gathering.
Wishing you all happy and healthy morning. Respected deans, esteemed guest, Dr. Gi Chun La, faculty members. I'm delighted to extend a warm welcome to all of you on behalf of the Department of Mathematics PG, Piyushya Krishnammal College for Women, Coimbatore. It is indeed a privilege to have you all here today as we gather for the third day of a 5-day international virtual FDP on mathematics and its application. I would like to extend a heartfelt welcome to our respected Dean, Dr. L. Lakshmanan, Dean, Mathematical Sciences, whose guidance and support have been invaluable in making this FDP a reality. The world is interconnected. Everyday math shows these connections and possibilities. Graph theory, the study of points and lines, has a history which may be specifically traced to 1735. Graphs can be used to model many types of relations and process in physical, biological, social, and information systems. Many practical problems can be represented by graphs. With the help of graph coloring concepts, it is possible to solve various timetabling problems, scheduling problems, team building problems, etc. This 5-day FDP paves way to enrich knowledge in various fields of application of mathematics. At this illustrious moment, I would like to join with the gathering to happily welcome our esteemed chief guest, Dr. Gi Chun La, Adjunct Professor, VIT, Malaysia. Welcome, sir.
Yeah, good morning and welcome.
Happy, sir. Dr. Gi Chun La has a sound academic qualification, which includes UG degree from Iowa State University, USA, PG degree from University Putra of Malaysia, where he was awarded PhD for his research contribution in the field of graph theory. With his academic excellence, he has more than 25 years of teaching experience with teaching interest, which includes the subjects like ordinary differential equations, calculus, linear algebra, discrete mathematics, business mathematics, etc. As a part of research, Dr. Gi Chun has more than 80 publications in various journals like Journal of Mathematical Sciences, Discrete Maths, International Journal of Mathematics and Combinatorics, Malaysian Journal of Mathematical Sciences, International Journal of Graphs and Combinatorics, and also an active research supervisor for many PhD scholars and students of MSc program. With these short notes, it gives me immense pleasure in once again welcoming each one of the gathering for today's session on the topic construction of local anti-magic three colorable graphs of fixed odd size matrix approach by Dr. Gi Chun La. Sir, the session is yours.
Thank you. So I would like to
Thank
share
you for
my
the introduction, ma'am.
So can I share my screen now?
Yes, sir.
Okay, can you see my full screen, everyone?
Yes, sir, it is visible.
All right. I need to minimize. Okay. All right. Okay, very good morning, everyone. And probably good afternoon to some of you here. I'm so happy to be able to join all of you here on this 5-day International Virtual FDP programs. And I'm so happy that I'm able to share some of my knowledge on some research problems that I have done over the last few years. Actually, over the last 20 over years, I have been working on various types of graph coloring problems and also labeling problems separately until about starting 2017, when I encountered these new types of research problems that combine the concept of graph coloring and labeling. So since then, I've been working almost all my research hours on these type of problems. And so the best way to remember me probably is to think of the GCL here as the GCL of the graph coloring and labeling. Yeah, okay. I think I want to stop my video so that everyone can focus on the slide, yeah? Okay. So here I'm going to share with you actually some of the results that I've obtained over the last few years and also some of the latest results I obtained a few months ago. Okay, so it's probably a very big difference compared to what we have listened to over the last 2 days talk. So this is research that I carry out together with 3 other researchers, one from Hong Kong and the other 2 from India. And especially I want to dedicate this to actually Professor Lee on the occasion of his 80th birthday, because he is the one that bring me to the beautiful field of graph labeling. So I believe that most of us already have basic knowledge in graph labeling and in graph theory and also coloring actually. But still, I want to go through some of the basic notation and definition quickly, yeah? Okay, so as usual, we know a graph G has a vertex set V and edge set E, which may be empty. Over here, I'm going to always assume that G is connected unless stated otherwise. And I'm going to say that the number of vertices is the order and the number of edges is the size. And we know 2 vertices, U and V, are adjacent if UV is an edge. There's an edge joining vertex U and V. And you say, we say that U has degree n if it is adjacent to n distinct vertices. So here, easily we can see that we have a graph on the left-hand side that we call it a fan graph. And on the right-hand side, we call them, they are all the view graph. So actually, they can be viewed as a joint of two graphs. Yeah. So what is joint of two graphs? Is the graph obtained from two different graphs, say G and H, such that every vertex of G is adjacent to all other vertices of H. And so the left-hand side graph, the fan graph, is actually the joint of a path and one isolated vertex. And the view graph is the joint of a cycle and one isolated vertex also, yeah? So the ON is the null graph order N. And I may use this notation of square bracket AB to mean the integers from A to B. So as usual, a proper K coloring or just coloring is just a vertex coloring using MOS K colors so that no adjacent vertices get the same color. And we say a graph G is K colorable if it emits a K coloring. And so this is a Peterson graph that emits a 3 coloring. And the smallest such K is the chromatic number of G denoted chi G. So now I want to introduce to you the concept of magic and anti-magic labeling. Yeah? Many years ago, the concept of magic labeling was introduced. So we begin with a set of positive real numbers, say R plus. So an injection F that label the edges with numbers in this R plus is magic if the induced vertex label of every vertex is a constant. So what is the induced vertex label? It's the sum of all the incident edge labels. And sometimes we say this graph G is super magic if the set of integers we use, or no, I should say set of numbers we use is a set of integers from 1 to the number of edges. So by definition, we all know the K2 is magic, but easily we can say that all cycles, or more generally, we can say every graph with 2 adjacent vertices of degree 2 must not be magic. And so the characterization of all magic graph has been done back in 1980s. The simplest way to get one possible magic graph is by using magic square. And that's why we call this a magic graph, because we borrow the term of magic from magic square. So then in 1990, Hartsfield and Ringer defined what we call anti-magic. So now the labeling of the edges is again using integers from 1 to the number of edges. But what we want is for every 2 distinct vertices U and V, they must have different induced vertex labels. And so easily again we see P2 is not anti-magic. But then all cycles and paths of order at least 3 are anti-magic. And this is another simple example showing that this graph emits what we call anti-magic labeling. But still, this problem is far from completely solved. So we still have 2 very famous conjectures in which we believe that every connected graph other than K2 is anti-magic. And this applies to every 3 also. Then, back in 2017, we have 2 groups of researchers. One is led by Arumugam and the other one by Ben Smith. Both of them independently introduced the concept of local anti-magic. In this case, again, we still label the edges as before for anti-magic, but then what we want is for every 2 adjacent vertices U and V, they must not get the same induced vertex label. In other words, if they are not adjacent, they may get the same induced vertex label. And so every anti-magic labeling is also local anti-magic, but the other way around may not be true. And so Arumugam et al. Also conjecture that all connected graphs except K2 are local anti-magic, and this was proved quickly in 2018. And so now today we can say that every disconnected graph without K2 component is also local and magic. Okay. And this diagram show two different graphs. They are related to views actually. They emit, okay, a local anti-magic labeling. As you can see, no two adjacent vertices get the same in this vertex label. So here, if we assign the in this vertex number or in this vertex label as a color of that vertex, then we get a proper coloring of the graph actually. Okay. And so if we say CF is a number of distinct induced colors under F, then we can say F is a local anti-magic CF coloring of G, and G is local anti-magic CF colorable. And so Arumugan et al. Define what we call local anti-magic chromatic number of G, that I'm going to call it Kyla G. Okay, and this is the mean value of C of F over all possible local anti-magic coloring F of G. So our two graphs just now actually have Kyla equal to 3 because they are tripartite graph. Okay. So by definition, it's easy to see that Kyla G must be at least Chi G. Okay. So this provides a very good lower bound in determining the exact value of Kyla G. And over the years, together with many of my collaborators, we have obtained many results on Kyla G. So for example, we managed to show that if G has K pendant vertices, Kyla G is at least K plus 1 and the bound is sharp. And if G is a connected bipartite graph of equal partite set size, then Kyla G is at least 3, although the chromatic number is 2. Note that if G is not connected, then this conclusion may not be true. Yeah. Okay. And we also show that for each possible nk here, where n is the order of G, we can always find a graph G with Kyla G equal to n minus k if and only if this expression is satisfied. And then for a spider graph of KLX, from number 1 here, we know that it has Kyla at least k plus 1, and we managed to show that the Kyla is at most k plus 2. And we also obtain many conditions so that the bounds, both of them, hold. Okay. And then, of course, we also have results on cycle, path, and fan graph. And also complete bipartite graph, completely solved. And also, we also completely solved the Kyla for this 1-point union of R copies of cycle. Okay. Yeah, we found that for it to have Kyla equal to 2, there are only 2 possible families of graph satisfying the condition here. Otherwise, Kyla is 3. And more than 1 year ago, we also completely characterized S-bridge graph with Kyla equal to 2. But for this type of graph to show that it has Kyla equal to 3 or larger is a very tough problem that we have only obtained partial results. So maybe I want to share with you 2 simple results together with the proof. So here, the first one is if I have a graph G with size Q and K pendant vertices, just now I already said that Kyla must be at least K plus 1, right? And the bound is sharp. In fact, this is achievable only if Q is assigned to a pendant edge. So the proof is very simple. Suppose you have a pendant edge UV and you assign with Q, because Q is the largest number you can assign, you can use. So here, if you assume U is not a pendant vertex, then U is of degree at least 2. So the induced vertex label must be the Q plus another number. So it must be greater than Q. But for every other pendant vertex Z, okay, the induced vertex label is just the incident edge label, which must be no more than Q. Okay. And by definition, all the induced pendant vertex must have distinct induced color. No? And because of this, now we have altogether K plus 1 distinct colors. And so the Chi-La must be at least K plus 1. And if Q is assigned to a non-pendant H UV, then both U and V have degree at least 2. And so yeah, in this vertex label must be greater than Q. And because Q is assigned to a non-pendant edge, then every other pendant vertex we have in this vertex label are less than Q. And so we have altogether at least K plus 2 colors. And so Chi-La must be at least K plus 2. Okay. And for sharpness of the bound, we have this example here. When K is at least 2, we can either use the spider graph, or also called star graph, SK with K pendants. Otherwise, using this left-hand side bottom graph here, by adding more edges, as many as you want, we can also make the same conclusion. Okay. And for K equal to 1, we have this example here. Okay, then this is another simple result that I mentioned just now. We say that if G is connected by bipartite graph equal bipartite set size Chi-La is at least 3. So here, we can assume that the bipartite set A and B with vertices xi, yi of same size, okay, size T. So suppose Chi-La is 2, then every vertex xi has in this vertex label say A, and every vertex yi has in this vertex label say B. They are not the same. Okay, but then by definition, you can see that, okay, actually by summing up all the in this vertex label of the vertices in the same bipartite set, that value actually is the sum of all the edge labels. Okay, and this is true for both bipartite set. And that means what? That means left sum equal right sum, but left sum is T times A, and right sum is T times B, which means that A equal to B, and this is a contradiction. Okay. All right. So basically, if you have a experience of doing graph labeling problems, what we normally do is we may begin by finding necessary or sufficient conditions to rule out some impossible cases. And then, for my personal experience, I sometimes, or I should say most of the times, I like to begin with try and error on small order graph. If I'm able to get the labeling that I want, then only I try to extend it to a more general case. And over the years, out of the many results that I have obtained, I noticed that there are quite many of them. Actually, I can get my labeling by using matrices. I use matrix to fill up the integers that I want to use. From there, I can come up with a labeling that I want. And the first type is matrices with empty cells. And I use it very successfully for bipartite graph, in which actually we want to prove this. For n at least 3, there is a graph G of order n with Chi-La equal to 2 if only n is not 3, 4, 5, 7. So Chi-La equal to 2 means that this graph must be bipartite. And I have to divide them into different cases. And for one of them, say n is 15, the matrix is something like this. This graph has 15 vertices. It's a bipartite one with one side of 3 vertices and another side of 12 vertices. So you can see here, every column here has the same sum, 25. Every row here has the same sum, 1, 2, 6. And every column represents a vertex of degree 2. Every row represents a vertex of degree 8. Okay, and so easily you can immediately conclude that this matrix correspond to a bipartite graph with Chi-La equal to 2. Okay. Next, I can also use it for tripartite graph, actually. In fact, we also show that the complete tripartite graph K1 to R is Chi-La equal to 3. And when R is 3, the matrix is a simple one, something like this. Okay. When R is larger and larger, of course, we have more complicated matrices. So here, row 1 and column 1 numbers or entries correspond to the edges, edge labels. Edge labels are incident to the degree 5 vertex. Okay, incident to the degree 5 vertex. And the row 2, row 3, they correspond to the edge labels incident to the 2 degree 4 vertices. Whereas the column 2, 3, 4, they correspond to the 3 degree 3 vertices. Okay. So easily again you can conclude that this graph is chi-la equal to 3. Note that so far we always have chi-la equal to chi. Chi-la equal to chi, the chromatic number of the graph. And then for tripartite graph, I also proved that these are the joint graph of even order cycle and an even number of isolated vertices. There's chi-la equal to 3. This is a tripartite graph, yeah. Okay. And method I use is matrix plus non-matrix approach. Here, what we do is I label the edges of the cycle C2n using 1 to 2n naturally, in natural order. So here I show you the example for C8. So the vertices will be U1 to U8. And I label the edges here by 1 to 8, naturally and consecutively. And then for the remaining edges joining the vertices of the C8 and the O8, I use a table or something like this, or you can say it's a matrix or table. And I divide the vertices U1, U3, U5, U7. Okay, put them in one part, and then the rest put in another part. Okay, because if I want to have a chi-la equal to 3, I must make sure that the vertices U with odd subscript has 1 in this vertex label. Those with an even subscript has another in this vertex label, and all the remaining vertices of the isolated vertices O8 must have the 3rd in this vertex label. So you can see here I fill up these tables using integers from 9 up to the 72, the maximum I can use. And they show a very nice pattern except the first part here. Okay? The rest all either in increasing order or decreasing order, or all odd or all even. Okay? And you can see the sum here for every row here. The row sum is not the same. Okay, but then together with the edges, with the labels from C8, okay, you can actually get that these first 4 rows sum, you have the same numbers together with the edge label, yeah. Okay, and the next one also, and also for every column, you can easily show that they have the same column sum also. In general, you are able to show that these 3 numbers must be distinct. So that means the chi-la is at most 3, and because the chi is 3, therefore chi-la is equal to 3. Okay. And then I also use matrices with repeated entries. Okay. And this is applied to what we call this a view graph. The view with 4k plus 1 vertices. Okay. So when k is 1, I have W4, which is this one. Note that each one of these has chi equal to 3. Yeah? So I suspect that it has chi-la equal to 3. So when k is 1, I use trial and error. Probably within 20 minutes, I can get a labeling that I want like this. Okay. But then when k is 2, it took me so many months to get this labeling that I want actually. In fact, I tried so many different possible ways until finally I come up with this method of using 2 different matrices with repeated entries. At first, I didn't use this method actually. So after trying for a few months, then only I come up with this idea, and I decided to use this idea, and I managed to get what I want. Why I have to use 2 matrices with this what we call repeated entries is because every number here on the outer edges, each of them belongs to 1 vertex on the left and 1 vertex on the right. Okay, and so this is the table, the 2 tables I use. Okay, so the first 2 rows, they have the same integers actually, same set of integers, just that in different orders. On the third row, of course, all are distinct. And the easiest way is to look at the example when K is 3. Okay, so this is a table. And what I do is actually I still have to do a tracing of this sequence. So I begin with the first column here, 1 to 9, and then I move to 9 and go to 5. So I pick up the 5. So I have 195. And then I go back to table 1, I begin with the one with 5, and then I go down to 7, so I pick up 7. And I go to the next one, next table, I see the 8, so I pick up 8. And so on until I collected all, okay, from the first 2 rows. And then I label these edges, okay, to the outer edges of this cycle. Actually, in any, what we call this arbitrary order, what we call clockwise rotation, yeah, okay. So 5, 7, 8, and so on until 11. And what we do to these inner edges here, so what I see here is 1, 9 together with 24, so I put 24 here. 11, 1 together with 17, so we can see here, where is my 11, 1? 11, 1, so here I put 17. In fact, you can see every column here has the same vertex sum in table 1. Table 2 also, every column has the same sum, okay, column sum. And column sum in table 1 is not the same as column sum in table 2. Okay? So they correspond to the induced vertex level of the vertices here. And the inner vertex, of course, I use the largest possible label, so the sum must be the largest. So all the 3 numbers must be distinct. Okay? All right, so a few months ago, I started to think of this problem. Can we use a single matrix of size A by B? And now I only want to use entries 1 to AB. No repeat, no empty cells. Okay? And I want to use this matrix to obtain local antimagic labeling of certain types of graph of size AB. And this must allow me to determine the local antimagic chromatic number of the graph that I want to create. And yes, probably I should say is I'm very lucky that I managed to find something that I want. Okay? So from now on, I will show you the result that I've obtained so far. Half of them, actually, I should say half of them, because only based on odd size graph, not yet even size graph. Okay? And all the remaining results that I'm going to share with you here will have chi-la equal to chi equal to 3. Okay? So first of all, I look at 5 by 2k plus 1 matrix. Okay. And so the number of cells is 10k plus 5. So I need to fill up the integers from 1 to 10k plus 5. Okay. By example, you can see actually it's quite easy to do so. All these odd, all this even. And then these go up consecutively from left to right, and then also here, from left to right. And then this one, sorry, from right to left, right to left. And then this one is from right to left all the way, okay? And then this one again, odd again, even again. And then this one, okay, this one something special. I go from left to right, left to right. But here is starting from this right-hand side part, then only go to left-hand side part. Okay. So what is so special about this matrix? You can see the first 3 row entries of every column has the same sum. Okay. These 3 numbers sum to 42. These 3 numbers also sum to 42, and so on. And then for each column, the sum of the first and the 4th row, respectively 2 and 5th row entries must be this number here. So 1 to 45 is 46, 4 to 42 is 46. Similarly, 1432 is 46, 1135 is 46, and so on. Next, I also have the other what we call observation. the sum of the last 3 row entry, okay, from column 1 to the last column, always form an arithmetic series, okay, or I should say arithmetic sequence. I think I typed wrongly. It should be arithmetic sequence. The first sum is this number, and the last sum is this number in decrement of 2, okay, increasing by 2. And I think I can skip number 4. Number 5 here, the sum of all the last 3 row entry is the constant, or the last 3 row entries here is a constant, given by this expression. We shall need this one later on, yeah. And the last observation is this, if you can divide 2k plus 1 into R blocks of S column, okay, in which the first block is the first S column, okay, second block is the next S column, and so on, okay, then actually you can see that row 3 entries in the J column and the row 4, row 5 entries in the R plus 1 minus J column. I should say block, not column, and block. In the J block and the R plus 1 minus J block is always the constant for all possible J. Okay? And there must be a one last block in the middle, okay? And all the last 3 row entries of this block also have the same sum, okay? So if you take RS equal to 3, you have 3 column block here, another 3 column blocks here, another 3 column blocks here. So yeah, these 3 numbers together, these 6 numbers, the sum is the same as these 3 numbers together with this 6 number is also equal to the sum of all these 9 numbers here. Something like this, okay? All right, so now I'm ready. I'm ready to define my new graph. Note that I already put down every column here correspond to, every row here correspond to an expression or a function, FUI, WI, FBI, WI, and so on, yeah? Okay. So now I can define a type of graph there, which is the n copy of P3 join O1, and I call it fan graph with n blades. I denote it by FPN. So if I choose n equal to 1, of course I get the fan graph F3 of order 4, yeah? Okay. And now I let the vertices of the IFB1 to be this. Okay. And then the edges are given by this. Okay. So I can have this theorem here. The fan graph with n blades actually has scalar equal to 3 when n is odd. Okay. Use this example here. Okay. So this is my U1 vertex, U2 vertex. This is my W1 vertex. This is my X1, X2, X3, and so on. I just need to label the edges according to the given table. So this U1 vertex and W1 vertex, okay, give me a label 1, come from here, U1, W1. When I is 1, I have U1, W1, and I see the 1 here, so I put 1. Okay, so you do the same thing for all of them, you can get this labeling. You can see here, every degree 2 vertex here, they have the same sum. Which is 46. Okay, just now I had mentioned the sum 46. Every degree 3 vertex here also has the same sum. Okay, which is 42. Yeah. Okay, and then every vertex x1 until x9 here, if you find out the sum, they are in decreasing order with difference 2. I have mentioned this also. So now if you combine all this, I mean, you merge all these vertices x1 to x9, you get the graph FP9. FP9. Use some imagination, yeah, because it's a bit complicated to draw the actual graph FP9. Right? So I decided to display it in this way. And of course, I don't explain the proof to you, okay? But I just want to point out that the induced vertex label will be the 10K plus 6, 9K plus 6, and this number here, okay? This sum is what I have mentioned earlier, actually, yeah? Okay, so easily you can see all these three numbers must be distinct. And so we can immediately conclude that it has Kyla equal to 3. In the same way, we can also define R copy of FPS. R copy, every copy is a fan plate with S, fan graph with S plate. Okay, this is by using the partitioning of the table into R blocks of S columns, R blocks of S column, each one. Okay, so what I do is actually I can partition the what we call the induced vertex label of x1 until x2k plus 1 just now, okay, into a magic rectangle with a constant row sum. And so I just need to merge the x vertices, x1, x2, x3 vertices correctly to get the new x vertices with the same induced vertex label. And the induced vertex label will be still 10K plus 6, 9K plus 6, and another one is S times 21K plus 12. And again, easily they are all distinct. Okay. So using the FB9 or 9FB1 just now, if I partition them into these three sets, okay, I can merge vertices in these three different sets here. I get the 3 copy of FB3, yeah. Okay. Now, this is the graph that I get actually, without the actual labels, okay, without actual labels. And there is another way to create a new graph with similar conclusions. What I see here is, you see all the degree 2 vertices have the same, what we call in this vertex label. So I can partition all these same degree 2 vertices into blocks of same size, okay? And for each block, I merge all the vertices to a new vertex. Now, as long as I choose the vertices properly, then the new graph I get will not have multiple edges. It will be a simple graph without multiple edges. And easily, based on what we have already known, all these new vertices will again have the same induced vertex label if I keep all the edge labelings. Okay. And so I will be able to get a new graph with also Kyla equal to 3. Of course, I can do the same thing to the degree 3 vertices. Okay, degree 3 vertices. Right? And so I have this result here. I use the notation FB1 RS to mean those from R copy of ABS, okay, by merging vertices in degree 2 of degree 2. Okay, this one is not a general partition because I take all the vertices together and merge. The general one is I can actually partition them into smaller sets. Okay. Anyway, this is what I get. The new graph, you have these 3 in this vertex label. Okay, and to show that they are all distinct, okay, I see that for the 2 larger numbers to be distinct, I need to apply this condition. Okay. And then for FP2 is on partition and merging of the vertices W, they are all degree 3. And I have these 3 distinct in this vertex label. And in similar idea, I can show that all 3 are distinct. And so this is the theorem I get. Okay. So first type of graph, I have to impose one condition. Second type, no condition. Okay, then let's say we only consider 2 FB3. I can create new types of graph that looks like this. Okay. So what I do is actually the kind of like switching the vertices. all the middle edges here originally join to this vertex here. I make them join to this vertex. The other way around also same thing. All the middle edges here, instead of joining to this middle vertex, I make them join to this middle vertex. And so I get a connected graph, something like this. If I keep the edges, I mean edge labels, this is what I get. No? Using the first and last three copies of the 9FD1. Okay. You can see that actually vertices of same degree still have the same in these vertex labels. Right? And this graph, I call it diamond fan graph because when I draw it, it looks like a diamond. Yeah? Okay. And from there, I can define a new type of graph that I call DFR2S that has R copy of diamond fan graph 2S and 1 copy of the FPS. Okay. And this graph actually has so many vertices of degree 2, degree 3, and degree 3S. Okay. And I can easily show that this graph has chi equal to 3. Okay. As long as R is at least 1 and S is odd. Okay. I show you the example. This is the one. Using the FB9 earlier, or 9 copy of FB1, I can actually create this graph. Okay. Together with the labeling, I keep the labelings. Then, although this part is a bipartite graph, but this part is a tripartite graph. No? So, Kyla is at most 3, but it's also at least 3. So the conclusion is Kyla is 3. And of course, using the same 9 copies of FB1, I can also take R is 4, S is 1 to get new graph with the same conclusion, Kyla equal to 3. Okay. So this is a very powerful observation actually. Okay. I can do the same types of so-called partitioning and merging of vertices of this DFR2S. Okay. To get new types of graph with similar conclusion also. All right. So I skip the detail here. In fact, there are 3 possible ways to do so. And using the same idea just now to show that the new in this vertex label must be not the same as the original existing 2 in this vertex label, I can get this. Again, first type, I need to impose a condition. Okay. Okay. So now, for 5 by 2K plus 1 matrix, I suddenly realized that if I rearrange some of the integers, I can actually use them to come up with new, more interesting types of graph. And what I do is actually, okay, wait. Yeah, from here, actually, I need to do what we call tracings of 2 sequences. Tracing of 2 sequences. Okay, the first one, S1, begin with these 2 entries, and then followed by these entries for all possible I from 1 to K over 2. Similarly, sequence S2. Okay, let's look at the simplest example. So the S1, what I do is I begin with this middle column. Actually, I always begin with this middle column. And then I take the first 2 entries from bottom to top, 8, 5, and then I jump to 21, 20, okay, bottom to top. And then I jump to 6, 4. So from left hand side here to right hand side here, 6, 4. And then I jump to 22, 17, come down here, and then go up 9, 3. Okay. So I do it the other way around for the second sequence, 18, 25, 1, 10, and 16, 24, and then 2, 7, and then 19, 23. Now that I have taken all the entries in row 1, 2, 4, 5, except entries in row 3. And I cannot recall how come I can come up with this type of graph here. I just cannot recall. In that day, I suddenly have this idea that why not I draw it this way? So when I draw it this way, and I assign the edges of S1 to the top edges here, sorry, I assign the integers in S1 to the top edges here. Assign the integer in the S2 to the bottom edges here. And then for the middle vertical edges here, I get from the row 3 here. So for example, 8, 5 belongs to column 3. So the 1 is 11. So I put 11 here. Okay. The next 21, 20, the middle is 13. So I put 13 here and so on. And you can see here, every degree 2 vertex, again, they have the same in this vertex label. In this case, it's 26. Okay, 26. Every degree 3 vertex, if they are adjacent, they must have the different induced vertex label. In fact, if you go from left to right, the induced vertex label alternate between the two numbers. Okay, so U1, U5, U9, and V7, V3 all have the same induced vertex label. V1, U3, V5, U7, V9 have another induced vertex label. It is not difficult to show that all these numbers must be distinct. You can do the same thing for the sequence when K is odd. K is odd. Okay. And because the drawing looks like, to me, is a very long peanut, so I call it peanut graph. Denote it by PTN. Note that this graph always has 3 cycles and 6 cycles. Yeah, so this case is PT6 now. PT4 PT4, and K is 2, N is 4 because N is 2K actually. Okay, so this is the sequence for odd K slightly different for the last 4 terms only. All right, I'm going to just show you the example here. K equal to 5, they have much longer sequences and much longer peanut. All right. Okay. So what is more interesting is the next one. Okay. Oh yeah, sorry, I should tell you the theorem first. Simple explanation of the proof is given here. Anyway, when N is 2K, whether K is even or odd doesn't matter. Okay, the peanut graph PTN is scalar equal to 3. Okay, because it is tripartite graph. Okay, so what is more important or more interesting is the next one. I can define a new type of graph that I call it triangular bracelets. From this peanut graph, what we do is I merge the X and Y vertices pairwise. Okay. No, I have only one vertex called X and one vertex called Y. So I merge them into vertex called Z0 and U2I, V2I, I merge them pairwise. Okay, to get vertex Z2I. Okay, and so this graph you have a lot of triangles. Okay, a lot of triangles. What I do is actually I merge U2 to V2, U4 to V4, U6 to V6, and so on until the last one, U20 to V20 here. And also the first X and the last Y are merged together to get a new vertex. So every vertex now is of degree 3 or degree 4. Okay? Degree 3 or degree 4, yeah. Okay. And I can easily also conclude that this graph has chi equal to 3. Okay, because I can keep all the edge labels. Okay? You can keep all the edge labels. So this is the example from peanut graph PT10. I guess I get this triangular bracelets T10. Note that the first and the last vertex should be joined together. Should be joined together. So it is in circular form like a bracelet. That's why I call it triangular bracelets. Okay, so and then I scan through all these labels and I find something very interesting actually. Okay, so if I don't give you any hints, probably you may not be able to see what is so interesting here regarding the labels. Okay. Before I go to that one, actually I have this Wait, I think oh yeah, I can have more variations. I can have more variation using a peanut graph and a triangular baseless graph. I can do a partitioning and merging of vertices like I have discussed earlier to get new graph with similar conclusion. I'm going to skip till here. Yeah. Okay. Yeah. Now here is the more interesting part. Okay. What is so special about this labeling here? Okay. So actually the special parts appear here, Z6 and Z12. The four induced vertex, the four incident edge labels are given here. Here. Okay. Can you see something special now? Can anyone tell me anything special here? For these two pays and these two pays, okay. No, the 1054 come from here, 46.2 come from here, 43.21 come from here, 13.35 come from here. Actually, they have the same sum pairwise. Okay, this and this same sum, this and this same sum. Okay, so what can we do about it? Actually, if you think of a way to cut this vertex into two halves and cut this vertex into two halves, you can combine this half here, right hand side half here, to the left hand side half here, and the left hand side half here to the right hand side half here. What you get? You get a graph with two components. And because of this equality, the new graph still have all the degree 4 vertices having the same induced vertex labels. That means what? That means actually you manage to get a graph with two components that are also triangular baseless with exactly the same induced vertex label as the original graph. So that it has chi-la equal to 3. Okay, but then when I search for this type of pair of vertices using larger n, I don't see that the Z6 and Z12 will give me what I want. Instead, they appear in other pairs. So there is no fixed, so-called fixed way of finding the pairs. It seems. Okay, so I decided to analyze further. Okay, what I do is the top edges together with the vertices of the triangular baseless, okay, I list down as a cycle. The bottom one, I list down as another cycle. And I found out that actually I can define a labeling function for all the edge labels. Okay, I can define it. So this one give me the edge labels for C1. Okay? The next one give me C2. All right, C2. Okay, so to get the induced vertex label, I have to sum up. Okay. This is only for the cycle C1, okay? And C2 separately actually, yeah? Okay, all right. So again, I want to look for the pairs, the sum, they have the same sum, right? Two pairs that have same sum. So when you scan through, it seems that not possible to find two different pairs with the same sum. Okay? Seems not possible. But then if you look carefully, these are the four that give me what I want. But what? I need to make sure that the I here change to 2i. The I here change to 2i. Okay? And then these two sum equal these two sum. Right? Okay. So now I change the I, the first two, the I change to j. The first two I change to j. The next two I still keep the I. So now you see, if I change my j to 2i, I get this sum equal to this sum. Okay? So From there, I can get the induced vertex label must be the same, satisfying the given condition. And when n is larger and larger, I have more than one possible paths to do the cut and merge. Okay? I have more than one possible path. In other words, when I have more paths, I can do cut and merge of not only applying to one pair. I can apply to more than one pair if I want. Then I will get more and more components. Okay? But then some of the vertices are in between the pairs that I have cut. And so in order to avoid this thing happen, I have to set two new conditions here. Okay? Set two new conditions to make sure that after doing the cut and merge, all the graph that I get must have every component is also a triangular bracelets. Okay. So these are just explanation. So I think I just keep them. Okay. Okay. So the new graph, I decided to name it as this. It is the graph with many components, or at least two components. Okay. Yeah, every component is a triangular bracelets, satisfying this equality, and these two conditions here. Okay. So here it is the graph. Just now I mentioned do cut and merge using the TB10. There's only one way to cut and merge. The graph is something like this. Triangular bracelets, right? Okay. And for larger end, of course, I have this. And I'm going to just skip through. There are more ways to do the cut and merge if you want. Okay. And same thing also for the graph, triangular bracelets, and the GN that I just defined just now. I can also do the so-called cut and merge to get more general solution. Okay. So I skip this part also. And the last final result is given by this table here. Now this table is not having only 5 rows, but what? How many? 11 rows. 11 rows. Also 2k plus 1 column. Even more complicated to find out this matrix here. But the result I get here is given by this example here. When k is 1, the simplest is this. And what I get actually is this theorem here. It can give me 2k plus 1 copy of P3 join O3. Our original first result actually is join O1. Join O1. Now it's join O3. Join with 3 different isolated vertices. More general than the first one. Okay, this is the example here. To get the graph, the actual graph I want, I still have to merge this x11, x21, x31 into one single vertex, x12, x22, x32 into another single vertex, and x13, x23, x33 into the third single vertex. Then it is the graph that I want. Okay, the 3p3 join O3 that I want. Okay. In fact, I was trying to extend it to more number of vertices, but still not yet successful. Okay. So here, actually, we have kind of completed another paper. Still need final tuning on even size graph. With the number of size is 10k. Okay. The matrix looks quite different. I mean the pattern, the way of fill up the matrix is quite different, but I am able to extend the result of FBN and RFPS to even values, even in variables here. Because now our results are all on odd one, right? This one even one. And surprisingly, I get even many more new bipartite and tripartite graphs. They are totally different. Okay? All of them also have the conclusion Kyla equal to 3, right? So some problems that arise naturally are listed here. Okay? And of course, from the known result, we already know this. NP2 join K1 is Kyla 3, PM join K1 is Kyla 3. So more generally, can we show that MPN join K1 is Kyla 3 also? Okay, so I hope the answer is yes. And of course, if you are able to find more general ways of constructing matrices like what I've shown you that can give rise to graph labelings and local and magic chromatic numbers, that will be a very, very great results for publication, of course. Okay, so I would like to share with you one of the best photo I have taken last year. All right, thank you very much for your attention.
Thank you, sir. Participants, if you have any queries, you can unmute and ask to sir, or else you can post it in the chat box also. Participants, do you have any questions? You can kindly unmute yourself and ask to sir.
I can see someone, I think, asking reference book, is it?
Yes, sir. They have asked about reference books. So any reference book suggestions, sir?
Okay, basically, this is still quite a new field of research problems about a local anti-magic chromatic number. If you want to get more, of course, the best way is to get from the papers that we have published, starting from the first one published by Arumugam et al. And also many papers that I have published so far. And of course, if you want, you may email me. Okay, you may email me or let me know later on. I can email you the papers that I have. No problems.
Thank you, sir. On behalf of everyone here, I want to extend my sincere gratitude for your enlightening and engaging presentation today, sir. Your insights on constructions of local anti-magic, three-colorable graphs, of fixed odd size matrix approach was not only thought-provoking, but also immensely valuable to all of us present. The expertise and passion was truly shown through, captivating our attention and inspiring us to delve deeper into the subject matter, and also the clarity with which you conveyed complex ideas, coupled with your engaging delivery, made for an enriching experience for all, sir. Thank you so much, sir.
Thank you very much.
Before moving on to the vote of thanks, I would request all the participants to kindly switch on your video for a group photo. I would kindly request all the participants. One.
Hello, I call upon Dr. P. Neeraj, Assistant Professor, Department of PG Mathematics, to present the vote of thanks.
Good afternoon to everyone. I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. Let me first of all start by giving glory of Almighty God for making today's session a resounding success. As Cicero rightly said, gratitude is not only the greatest virtues, but the parent of all the others. Today, I take this opportunity to express my deepest sense of gratitude and appreciation to all those made this FDP such a success. To begin, on behalf of Department of Mathematics PG, I would like to thank our resource person, Professor G. June Law, who spared the time from his busiest schedule to grace this occasion. We get a knowledge like graphs with content vertices, labeling with matrices in bipartite graph, matrix representation, and also peanut graph is very much interesting, sir. Thank you so much, sir. Next, I would like to thank our beloved Secretary Madam for her generous support for this evening. Your encouragement has constantly bolstered all our endeavors. Thank you, ma'am, for your unstinted support. Next, I would like to thank our principal, ma'am. Your guidance will be always help us, ma'am. Thank you, ma'am. My heartfelt thanks to our dean, sir, for his guidance and encouragement in all our efforts. I would like to express my thanks to our lovable HOD, who is pillar to our department. I express my special thanks to our team members for their cooperation in making this function a fine success. Last but not least, I thank everyone who have actively participated. Thank you, participants. Thank you, one and all.
Thank you everyone for joining us today. Kindly join us for tomorrow's session, which will start from 5:30. The feedback link has been posted in the chat box. Kindly fill the feedback form. Participants, kindly fill the feedback form and you can leave the meeting.
இது பாருங்க இது என்னன்னு மட்டும் சொல்லுங்க எனக்கு இத நோட்ஸ் கொடுத்துருவா இது வரைக்கும் எழுதுறதுக்கு இதுக்கப்புறம் எக்ஸாம்பிள் தான் போட்டேன்
Participants who have joined through YouTube link, kindly join again through Zoom link, and you can fill the feedback form posted in the Zoom chat box. You have having a technical problem in YouTube link, so kindly join a Zoom meeting and fill the feedback form in the chat box.